to dynamics. So, ladies and gentlemen, we're going to add a model. So, on the ground, 20 push-ups. How do we add a model? File, new model. Good. I like it. Okay, file, new model. Okay. This model is going to be called Simple Interacting Weight and Diabetes State Charts. I'm going to put an SK on the end because other previous version that I've used. Simple Interacting Weight and Diabetes State Charts, all one word. I use camel case. I capitalize the names of each successive word so I can read it. Okay. Great. Okay, so ladies and gentlemen, what we see before us a model. Can this model run in its current form? It can. Does it include a population? No. There's no personhood. There's no agent class here. There's a blank slate on which we will now write. Okay, so ladies and gentlemen, let us go add in a person class. How do I go add a person class? Right-click on the model, and then we could do add new, and what do I add? Agent type, and I'm going to add person. Okay, and do finish. Okay, great. Okay, so ladies and gentlemen, we wish to lend this person an appearance, and we're going to give them an appearance as a little person in this case. Okay. I'm sorry. In this case, I think I will still do for various reasons that we're going to tap into. I'm going to do an oval, and I apologize. We'll do some person-shaped things tomorrow. Okay. So how do I give this person an oval-like appearance? Drag it onto person. Okay, good. Okay, so I've just dragged it onto person, and let's do this here, and there we go. Okay, great. So now they have a set of persons. Okay, ladies and gentlemen, we want to add a population of people of size, say, 100. How do I do that? Okay, click on main, double click on main, so we see main, and then what do? Drag the person onto it. Okay, that's great. So let's suppose we call it population. What else do we have to do? Select population of agents here, and let's keep it 100, okay? Okay, great. Ladies and gentlemen, build early, build often. Okay, great. Okay, so what will happen if we run the model now? What will we see? Yeah, we'll see circles atop circles, almost Ptolemaic in its implication. So epicycles. So let's go and put these people so they're scattered around the space. This is not going to have logical implications now, but it will give the model the ability to parse it a little bit better and make them not occlude each other. So, ladies and gentlemen, how would we scatter these people? Well, let's run the model first. Let's check our intuitions for what pathologies will result. So, do we have a population of size 100 here? Okay, we do. It says 100, and we can drill down and we can go see each person. But let's go give them now a layout. So how do I lay them out randomly? Ladies and gentlemen, where do I go to lay them out randomly? Okay, good. Environment of? Okay, in which class? Main. It's in main. Okay. So then we scroll down in main, and and we go to layout type, and we choose random. Okay? Okay. Good. And you right-click here, and then we should see this. Okay, who needs TA help? The TA stand ready. Okay? Okay, TA help on the far corner. So folks, where are the other TAs? Okay. Okay. TAs, yeah. Okay, are they coming? Coming? Okay. 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 So this one over there. Okay. Who else needs TA help? Okay. Okay, TA help up here, front, middle. Okay. Okay. Robin, do you need? Okay. Okay. So, folks, we have this population created. Okay. Now we're going to introduce something new here. Okay. So we're going to go to person, and we're going to add a state chart. We want each person here. We want each person to have a state chart by which they will evolve. So maybe I'll just make a statement. I really want this to sink in with people, the very basic things we've just done, okay? Because we're going to be going through this again and again and again. I just want to go through the steps in your mind, okay? The steps are, number 1, add a new model. Number 2, add a person class. Number 3, add a presentation to that class. Number 4, add a population to main by dragging that person class into main. Number 5, indicate for that population that it's a population of agents rather than a single agent. Okay. Now, if you run that model, you're going to get that population, but it won't be visually laid out. You go to main, you go down to that area environment for other agents, and there's a choice of layout type, and you set random, and it'll show it randomly. And that's your baseline model. That's like your minimalist model to do something interesting. Okay? So that was just the overview, just to make it sink in. Okay. Okay. So, ladies and gentlemen, we want to now we want to go where we have not gone before. Okay, in this class. We're going to want to add state chart to capture a person's behavior over time. So double click on person. So double click on person here, and we're going to add in a state chart. So where we do this is down here on the left-hand side, a state chart. Okay? Okay. So this is in palette, and we're going to go to state chart here. And the first thing we're going to add in is a state chart entry point. This is going to capture a bunch of states that are mutually exclusive and collectively exhausted in evolution between them. So it's going to be called state chart. All right, let's call it diabetes state chart. Okay. Diabetes state chart. Okay. And we're going to drag in a state called, and it's going to be called normoglycemic. Statechart. Thank you, Trent. Statechart. Yeah. Okay. And then we'll set this to be normoglycemic. Okay, and now we're going to drag in another one. It's going to be, we're going to say diabetic. Okay, we're going to actually abstract over pre-diabetic state. We'll call that normal glycemic, okay? So maybe we should call it normal glycemic. Let's call it non-diabetic. We'll go back and edit this. Non-diabetic. Okay. Okay, non-diabetic. And then others is diabetic. And then let's set a transition between them. Okay, so this will be called developing diabetes. Now, you may wonder why give this an important name. Well, if you ever see the list of names, it can be useful to know which is which. But moreover, we can do show name here. If you click show name, it'll actually show the names of the transitions, and that will be self-documenting. And you can drag these around, okay? Okay. Okay. So here we have a state chart, and we're going to be able to set the type of transition associated with this to choose amongst a set of types of transitions. And I provided you with slides that discuss this in a little bit more detail, but there's several types of transitions. One is a timeout transition that occurs after exactly a certain time. And this is very handy if you want to have them transition after precisely some time, or if you want to draw a time, if you want to have a custom residence time in this state. In other words, you want to have their time that they spend in the state be drawn from an arbitrary distribution. You can set the timeout to be drawn from a distribution, and then they'll leave this distribution after a certain specified time is drawn from a distribution. A second one is rate, which allows you have a certain chance of leaving per unit time. It can be based on a condition, a certain condition obtaining, or say your age is greater than 18, or having received a message. There's also a final one under here that you can't see, which is agent arrival, meaning that they've arrived at a destination from a mobility context. So I'm going to say timeout, I'm going to say a rate transition, and for now we're just going to make this rate become 0.01. Okay? Okay. So they're going to have a 1% chance per year. Now, this brings up the time unit. Where do I go specify the time unit in this model? Can anyone say? It's up in the whole project. It's up in the whole project. So let's go up to the project. Time units is minutes, which we definitely don't want, and we're going to set it to the years. Okay? You notice there's also the capacity to specify units of measurement for space, for the spatial dimension. We'll use the unit system adopted by 3 of the 4 participating countries metric for now. No 3/16 of an inch here. Okay, so this is going to be years for our model time unit. Okay, ladies and gentlemen, I'd like to go run this model temporarily. Let's go run it, okay? And we can't see any difference, but let's go drill down to the level of a person. And you'll notice a given person, if we browse between the people, here we have a statement of the state that a particular person is in and a countdown given in the time units, namely years here, till the time that they will be developing diabetes. So this is shown by virtue of the fact that there's enough space between the lines for it to appear. If we drew these further away, it would, if we drew closer together, at some point this will disappear. Also, by showing this name, I believe that's required to also show that. Okay? So here we have an indication that that person will become diabetic at a certain time. If we scroll through the list of people, we'll discover that some people have become diabetic already. So we have this population, and these population are moving between different states. Okay? That's great. We have a first state chart. Okay, ladies and gentlemen, we're not going to stop here. Instead, we're going to add in an important risk factor for diabetes. Well, let's actually make this a little bit more visual. Okay? I'd like, ladies and gentlemen, to set there to have the color associated with that oval depend on the state that they're in. Okay? Okay, we're going to have the color depend on the state that they're in. So, ladies and gentlemen, let us go add in, for the first time, let us go add in a variable. So, from whence does a variable spring? From the palette. And where in the palette? In the General tab. So, ladies and gentlemen, we're going to go drag in a variable into this model, and it's going to be called color. Okay? It's going to be called their color. Okay? And we're going to set their color to be different depending on what state they're in. There's many ways of actually setting the color of that oval, but this is one of them that scales reasonably well. So, and the way we're going to do this is this color variable, we're going to need to make it encode a color. It's not going to be a double. It's not going to be an integer. It's not going to be just an agent. It's going to actually be a color. So we need to set its type to be other, and the type needs to be given by capital C LOR, just like that. Just like that. Capital C LOR. Okay? So this is going to encode some color. Okay? Okay. So now we're going to set this color variable when people come into this this state here. We're going to set it to be green. So when they enter the state, you'll notice we can specify an action when they enter the state. So we're going to say color equals green. And you can make it all caps or you can make it all lowercase. I'm going to keep it as capital. And I'm going to build early, build often. So I'm going to press that build. Okay, TAs, deployment in sector 1. Oh, yeah.
I noticed the equal sign got 1 equal, previous to that was
Yes.
2.
Thank you. Okay, so these mean very different things. 2 equals is to test, is this equal to that? And it returns true or false. We're gonna test, is A equal to B? Is the sex equal to sex dot male? Here, we're actually we're changing the value of color. You'll notice the semicolon at the end. This is a statement. It tells it to do something. We're not actually calculating a value here. We're actually changing something. We're changing color. We're modifying something. We're performing a side effect. We're changing the state of the world by changing our color. And hence, there's a semicolon after it. We're performing an action. Does that make sense? Yep. Okay. Yep. Okay. So we set that to be color green. Ladies and gentlemen, let us down here set, when they enter the diabetic state, let us set their color to be red. Okay?
Is there a reason you're typing that out instead of just clicking on where it says default color?
Yeah, it's because, it's a great question. Were it only so that setting this default color. So let's set the fill color here. So let's set it. I like it. Let's set this to red, and let's set this one to green. The fact is, if we do that, we could run the model, and you don't have to do it. I'm going to run it right now. We could run the model. It's not going to make a whit of difference for the actual appearance of people visually. So instead, we need to actually manually sort of tell it, okay, what color to be. This is just the depiction visually on the screen. Yeah, when you look at a particular person. Okay, the final thing we need to do, folks, is we've created a color. We've said when they're here, it should be green. When they're here, it should be red. What do we do to actually make it change the color of the oval? Go to the oval and set its fill color to be what? Could it be color? That's what we need to do. That's the magic step, to link the two together. Now we have the mechanisms to change the color, and we have the mechanisms to show it as the fill color of that oval. Okay, ladies and gentlemen, should we run it? Should we run it? Okay. Okay. So here we have people, and over time, people are becoming diabetic. Okay? Do you see that? Okay. Ladies and gentlemen, I'd like to show you something different. To illustrate these types of timeouts, I'd like you to go temporarily, we're going to set this timeout to instead be a rate to be a timeout. So this developing diabetes, I want to set it temporarily to be timeout of time 10, say, or time 100. So in both cases, they're going to spend a mean amount of 100 years before they become diabetic. Here I'm setting its timeout to be 100 time units, 100 years as a timeout. Previously, we had a 1% chance of going from here to here each year. It would take on average 100 years to go. Here we have a time unit of 100, meaning we go after exactly 100 years. Okay? Okay, who needs TA help? Okay, let's run this. What should we see different? Anyone? Okay, now they're actually going to change at the same time. So we're going to have to wait until it goes up to 100, and now we're going to go, boom. They're all changing at the same time. Okay? So there's a big difference between a rate transition, even though the mean is the same. The average amount of time that they spend in the non-diabetic state is 100 years here. But with a timeout, they change it exactly that time. Here they change it, have a certain chance per unit time of going. Okay? Okay. Okay. So, are people comfortable? Yes, Trent. Oh, okay, very good question. So I didn't show people this, but let's talk about it. So Trent just asked, when we had it, set it to a timeout of 100, and I ran it, that his was grinding along at a stately speed, whereas I sped mine up. I clicked up here to speed it up, and we can speed it up, and it will actually go faster. If we want to run it at maximum speed, then you can use it at this speed, and it will actually go at maximum possible speed. Those other speeds are set for human kind of ease of understanding. Does that help? Okay. Okay, folks. This is good. Okay. Great. So, folks, we're now going to implement one more risk factor, and it's going to be the crown jewel of our day. Okay? The crown jewel. Okay, so we're going to add weight as a risk factor here. So we're going to have a weight state chart, okay? So, ladies and gentlemen, we have a diabetes state chart. I want you to tell me how to construct a weight state chart where we're going to have 3 different states, normal and underweight, overweight, and then obese, and we're going to have transitions between them that are given by rate transitions. I'd like you to tell me how we're going to add that to this model. What do I do? Okay, go to palette. Okay. Okay, yeah, and what do I do? What do I drag in? Okay, you have to drag in an entry point. This is really important. Don't just start dragging in the states. Okay, so do weight state chart. Okay, and then let's add in 3 states. 1, normal and underweight. Ladies and gentlemen, make sure it's connected. It won't cut it if it's disconnected like that. You want to look till it turns green there. It's turning green and you're in business, okay? Let's make this normal and underweight. And let's drag in another state that's overweight. And let's add in another state that's obese, okay? Obese, okay? These are weight categories that are distinct from diabetes. Okay, and now what I'd like to do is, you'll notice it's showing me errors here. It's showing me problems. It says 2 errors here, and it actually complains in this problems window, which I can get to by clicking down here, down at the bottom. You can't see that, yeah. Let me adjust that. Okay, there we go. Okay, it's these 2 errors, right? Okay. So, ladies and gentlemen, we need to, by clicking those arrows, you could see we need to connect it up. So we need transitions. So let's select it, normal and underweight. Let's put 1 transition there, and this will be called becoming overweight. And then let's set a transition going back the other way. That will be called losing overweight. Okay. Losing overweight. Okay. And then let's set a transition to obesity, to the obese state. Call it becoming obese. Becoming obese. And let's set a transition back, calling it losing obesity. Okay? Losing obesity. 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 Okay? Great. Okay, now, ladies and gentlemen, what I'd like you to do is we're going to set these transitions, each of their properties. So for the first transition, becoming overweight, I'd like you to set a likelihood here of 0.04 as a rate. So it'll be a rate transition with 0.04. Okay? So the TA should note these. Rate transition of 0.04. Okay? For becoming overweight. And I'm going to show the name. Okay? For losing overweight here, I'm going to make it a rate transition of 0.02. Okay? And then for going from overweight to obese, I'm going to make it a rate transition of 0.1. And for losing, and I should show each of those. I should show the transition names, show name here. And then for going from overweight to obese, 0.1 weight. What does that mean? That means a 10% chance per year of becoming obese. 0.1. 10% chance per year. No matter how long you've been in that state, you have a 10% chance per year of going, if you're in an overweight state, of becoming obese. That's what that means. Okay? And going back, returning, I'm going to make it I'm going to make it a rate of 0.05. That means a 5% chance per year of losing obesity. Now, AnyLogic's time is continuous. So we have a chance within a year to be losing obesity, but this is a 5% chance per year as a density. Okay, So let's show this name also. Okay. Here, show name. There we go. You'll notice that the icons here are associated with each of these rates. The icons indicate the type of transition. Okay? This is the type of transition. You'll notice that here we have rate transitions. Before we had a clock, which indicated a timeout. Later we'll see message transitions, which are associated by something that looks like an envelope. And there's also arrival transitions, which are associated with a flag that's used in some sort of racing. Okay, so here we have our little state chart. Anyone want to ask questions about this? Yes. Something at the end, meaning? Oh, yeah. We're gonna. It's a good point. I'm gonna link this up to their developing of diabetes. Okay. So right now, ladies and gentlemen, we have two state charts. This is actually a non-trivial point. We have state charts that each indicate different aspects of their evolution with respect to diabetes, their evolution with respect to weight. And let's run this thing, and we'll see people over time evolving with respect to each of these. So we run, and we drill down, and here we see someone who's non-diabetic, they're normal and underweight. I'm going to scroll up here, and here's someone, for example, who's currently overweight. They're also diabetic, it looks like. They're down in this state over here. Now they're obese, and so they're changing. They have weight status and they have diabetes, and those are each evolving independently. In a stock and flow model, this would be quite messy to capture because we need to consider all combinations. Here we just need to consider each of them in a fairly modular way. Okay, Bahare, I was wondering if you could help Hua come up to speed here, and also help Sarah here. So here we have these two state charts. These state charts are associated with weights. And the next thing I want to do is, these state charts are solitudes right now. We want to couple them. Yes. Okay, yeah.
What are the numbers that it's showing under the different, like overweight? Is that...
You mean how it's counting down? Yeah. It's countdown. It's the amount of time it will take until they leave with that transition. It's interpreted. So there's a great question here, folks. Let's go look at it. So, folks, you'll see here. What's the buzz? So there's a lot going on. Okay. So here you'll see countdowns occurring. What this is indicating is this person will next be leaving, unless something else happens, like they get a message or the model ends, they'll next be leaving via this transition here. This person will be going from non-diabetic to, in 58 years, this person in 6, and the countdown is here, and in just a minute, they're going to go to overweight, and now they're going to go back here in 31 years. You'll notice it's actually calculating when they're going to be leaving that, when they come into that state. This is significant, as we'll discover in just a minute. Okay? Yeah, George.
So you're talking about them leaving, tentatively going back in that other direction, but they really can go in two directions. They can go from overweight back to normal, or they can go up to obese. And both of those are sort of competing probabilities.
Those are competing risks, and whichever them is scheduled, it'll be, when they enter the state, it'll be, these are rate transitions, and it'll be calculating which of those will go first. These are, at a technical level, these are exponentially, it's exponentially distributed residence times associated with one of those alone, and it will be basically figuring out which of those would occur first, and that's the one that's highlighted. So this one is going to be occurring first before this one. See that? So these are both counting down, but this one is slated to go before this one right now. And so this one is going to be the next one they're going to take, all other things being equal. Now we're going to see that later We can have messages and they'll go a different direction, but here they switch to obesity, and therefore that one's never going to get a chance. That competing risk, if we can call it really a risk, that competing event is going to be descheduled. It's not going to actually happen. This is important because you can imagine someone, say, who has diabetes, and they can either die or they can go on to develop complications, and there's going to be competing risks associated with each of those. And whichever those occurs first will be the one that in fact happens. Does that make sense?
Yeah, I mean, but you would normally build both of those with probability distribution.
Correct.
So they really could go either way.
Totally. Yeah. Yes, you could associate these with distributions that we based on risk factors of the particular person and so on. Okay, so ladies and gentlemen, we're nearing the end of our example, but I would highlight the fact that these are solitudes right now. These are two solitudes. We have two state charts, and that's great to capture aspects of a situation. Captures their evolution over time with respect to different attributes, but they're not informing each other. They're not they're not interacting at all. And so that's what we're going to do now, and you are going to help us determine how to do that, because you have all the pieces to the puzzle. So, ladies and gentlemen, how did we capture it so that they changed color when they changed their diabetes status? Can anyone tell me? Sorry? Yeah, there was an entry action. What did that entry action do? When they entered the state, what happened? They changed the value of this color variable. And when they become diabetic, it changed the value of that color variable again. Did it not? It did. So in this case, let's suppose we want their weight status to determine their likelihood of developing diabetes. In other words, let's suppose we want the hazard, the chance per unit time per year of developing diabetes to be dependent on their state. How could we accomplish that via a similar mechanism? Could anyone think about that?
Some variable, instead of the 0.1, you've got some variable risk, or variable rate, I should say.
Good. So we could have a variable rate, a chance per year of becoming diabetic that depends on their current weight. Could we not?
Can't we just put a transition arrow there? Transition from obese to diabetic?
Well, but then you want to keep track of their obesity, their weight status, and regardless of what their diabetes status is, you want to have them have a weight status as well. Among other things, if they're diabetic, it might help improve their glycemic control if they lose weight. So this is a mechanism we have now which allows them to simultaneously maintain information on weight status and on diabetes status. So we wouldn't want to just say diabetes is a progression from obesity, because then we wouldn't know what the weight status is of a person with diabetes. Does that make sense?
Yeah, I was just wondering, to me, logically, it would mean a transition, and then you tell us what percentage of people who are obese.
Okay, but here, no matter what, like someone who's overweight might also become diabetic with a certain chance. It's just a lower chance. It's a lower chance per year of becoming diabetic, but you could have someone who's overweight. I know of people who are normal weight and have become diabetic, and so there is some chance, and we don't want to preclude that entirely. So, ladies and gentlemen, we're going to adopt the strategy suggested here by John here and David, excuse me. I know John Reese too. And we're going to set it so that we have different rates of becoming diabetic different chance per year of becoming diabetic depending on the weight status of the person. Okay? So we're going to introduce a what into our model? A variable. Okay? And this is going to be called diabetes hazard. Okay? Diabetes hazard. And this is going to be a chance per year of becoming diabetic. Okay? Does that make sense? Does that make sense to people? A chance per year of becoming diabetic. And we're going to set it over here in these different weight status. Just like we set the color variable, we're going to set their diabetes hazard rate, the chance per year that they're going to develop diabetes, depending on the state that they're in this state chart, in this weight state chart. So when they enter normal and underweight, they're going to have a diabetes hazard of 0.005. Okay? A very, very low diabetes hazard. When they enter that state, we're going to set this variable to have a very low chance of per year of becoming diabetic. Okay? Ladies and gentlemen, we're working towards our crown jewel here. And humor me just a little bit. Okay? In the overweight state, our diabetes hazard, our chance per year of developing diabetes is going to be 2% per year. So while they're overweight, as long as they're overweight, they're going to have a 2% chance per year of becoming diabetic. Does that make sense? Are people comfortable with that notion? I sense residual discomfort. Unless this is my lunch. Okay, and then in the obese state, they're going to have a 5% chance per year of becoming diabetic. Okay. So we're almost done. The crown jewel has been sculpted, but not yet mounted. How do we mount it? How do we... So right now we're setting this variable, but that's full of sound and fury, and it signifies nothing at this point. Precisely. We have to make it operational. We have to change the rate at which this transition from non-diabetic to diabetic becomes. Right now, it's doing a lot of work, but not really meaning anything. It's not accomplishing anything. We need to set this transition to go from developed non-diabetic to diabetic to be what? Diabetes hazard. Okay? Yes.
Could you have done this without using the variable diabetes hazard and just go directly to the rate and say
I could have. Yep. There's trade-offs either way.
Yeah.
I happen to feel that this is a little bit more transparent than writing the long expression for figuring out the rate. If I used a function, it would be a little bit more transparent, but I don't want to introduce them this early, so it's a balance between things. This is a fairly clean way of doing it, and it draws directly on this idea of setting the color variable. So it has a certain unity to it, thematic unity. Okay? Okay. So ladies and gentlemen, shall we run it? Okay. So the crown jewel has been sculpted. It has been mounted, and it is in operation right now. But it is not yet polished, and we need one more step to polish it. Precisely. Vikram has polished the gem, the jewel that gleams in the crown. Okay, so let's change the size according to what, Vikram?
Normal, underweight, overweight.
Good. Exactly. Vikram, you're thinking like a computer scientist now. Okay, so I'd like to go down to And what do we add to our model to change the size? Suppose we want to change the size of that oval according to the weight state that they're in, as Vikram very nicely suggested. How could we do that? What would we add to the model to use the same basic approach? We could add a variable. We could add a variable, and let's call it, radius? Something like that? What do you say? Radius? Sorry? Yeah, we could say weight. I'd be tempted to say radius just to keep it a little bit more transparent. But people will differ, and I'll just say radius. You could call it size if you want to. Okay, now where are we going to set this? We're going to set it in. Well, every time they change categories here, we'll set it. So let's suppose in the normal and under rate, we'll set the radius to be equal to, say, 5, something like that, 5 units. Let's say 5.0, you know. And then here we'll set it to be the radius to be 10. Okay. And then for obese, we'll set the radius to be 20, something like that. Okay.
And is that the number of little squares in your grid?
Yeah, exactly. Okay, 20. So 5, Kurt, for the top one. 5, 10, 20. Okay. And ladies and gentlemen, where do we, that too is full of sound and fury, signifying nothing until we do what with it? Yeah. We're going to have to set it up here with this thing here. We're going to have to set it for the radius. Now, ladies and gentlemen, I want to highlight for you a common misunderstanding here. If I go and I try to type it in here in this interface, it's going to be very unhappy. I could try to type in radius here, and it will complain bitterly. So what do I have to do? I have to click this thing, and only then will it actually allow me to type it. Okay. Otherwise, it's a static quantity. Okay. Should we run it? Should we run it? Okay. Okay, can anyone give me some narrative? What's going on? Okay. Okay. Yeah, a lot more of the bigger circles are turning red. Why is that? Because they have a higher chance per year of developing diabetes. So what we see is a population that over time is developing obesity. Those that are obese, if we go down and we look at this, those that are obese, someone like this is more likely to be diabetic than someone who's not. Okay. So here we have a situation where we have, at a population level, we've captured kind of the interacting of two conditions. We've captured one factor as a risk factor, one dynamic risk factor, weight, as in its function as a risk factor for a separate factor, diabetes status. Okay. So here we have a one-way transition where essentially the weight status influences the diabetes. Now, of course, we can put in place the opposite feedback. So we could put, once someone has developed a chronic condition, suppose heart disease or chronic congestive heart failure, then someone with a later stage chronic disease, it might affect their physical activity levels and by extension their weight, and so we could have interactions the other way. Here we'll leave it like this way. What I've shown you is the ways in which you can describe multiple conditions for a person using state charts, and we can have those conditions interact with each other through variables, with one state chart influencing the likelihood of changing states for the other state chart. Okay? Yeah.
With the way that currently implemented,
yes.
with the changing rates for development of diabetes.
Yes.
As it changes the state, it's resetting the probability of when, say, you go to overweight, you got a new chance, and you go from overweight to obese.
Right.
But does that, though, reset the actual rate that's being used for diabetes? So
it does.
You say it could be going in 30 years to be
right.
diabetic, and all of a sudden you go to obese.
Right.
And all of a sudden you end up with a new 50 years to
right. Right. Okay, so there's two ways I can answer that question. The answer is it does. It's actually recalculating. So the question as I understood it was, okay, well, that's all very well and good that we set this diabetes hazard based on our locations in the state chart to the right, but is it really impacting our likelihood of becoming diabetic? For example, we may have started a normal weight state chart. That set our likelihood per year of becoming diabetic. And has it really changed, when we're going to become diabetic just because we're changing this variable? Is it really recalculating? And the answer is it is. And there's two simple tests we could do for that. One would be everyone here starts normal and underweight. We could set it so that in that state you have no chance per year of developing diabetes. And you'd find still people are becoming diabetic. So that'd be one way to check. Another way would you get it to actually call a function here when it calculates this rate. And so instead of directly getting this call, get current diabetes hazard, and have that function print out something, say I'm being recalculated, and you'd find it's actually recalculating it here. It's recalculating when it's changing states.
So the recalculated could actually be much larger than they were before. So
yes.
So an overweight person
that's correct.
Could potentially, when they change transition, end up with a longer time till they end up being diabetic.
It's possible.
So
yeah.
you need a more complicated function if you want to have some sort of
right. Right. If you wanted to sort of retain that existing risk or what have you. Yeah, that's true. It redraws from that distribution. Yeah. That's a good question. And as a general matter, ladies and gentlemen, when you change state with respect to one state chart, it will recalculate the rates in that state chart and other state charts. And as a general matter, if there's things going on in a person which are not related to that, it won't be actually recalculating this, and you may sometimes have to force it to recalculate by putting an internal transition here. And we'll see that tomorrow. Okay? We'll see that tomorrow. But this is an introduction to state charts. There are several types of transitions. We've seen two main ones: timeout, which we saw in our very first exercise, and rate, which we also saw in our very first exercise. We've seen how we can make rates for one state chart depend on the states of another state chart, and we've seen how we can capture visual interactions that depend on state chart and presence in a certain state chart. This is the substantive area, and like a lot of areas in the boot camp, I don't have a chance to go into a detail. We'll be seeing quite a bit more about state charts tomorrow when we look at messaging and one agent interfering with another agent through the use of messages. We'll see that state charts form a key asset when capturing those interactions. But are there any questions right now on these state charts? Yes, Robin.
So the way that we have it here, when
yep.
somebody becomes diabetic,
yeah.
but they lose weight, they go to another weight category, they'll stay diabetic though, right?
They do, yeah.
Okay. We don't have, unless we had another transition that went backwards that said,
right.
if you lost weight or something, you have a chance of sort of recovery.
Right, and there actually is epidemiological evidence that I know of that where there are cases of people who are diabetic recovering. It's quite rare, and it's often under quite extreme circumstances, like the sugar embargo associated with Cuba, and in cases of starvation and so on, people have been known to lose type 2 diabetes, but it's a rare circumstances, and so we haven't captured that here. Okay, other questions? Okay, so we've just built up our first model. No, we built up our first 2 models. You're to be congratulated. This is not easy, and I know there's a lot going on here. I'm trying to weave in a couple components so that we'll get a chance to exercise them again and again, and I know that means there's a bit of a cacophony of ideas here, but I hope the basic ideas from this afternoon have been fairly clear about heterogeneity captured through parameters, ability to set a model as a whole to use parameters, and then with state charts being able to capture people being in a given state with respect to a single state chart at a time, and then transitioning between states over time, being able to capture multiple types of that evolution in different state charts, and having those state charts interact. There's a lot of advanced things we haven't seen. More sophisticated stuff with types of transitions, using custom distributions when we have a timeout transition to impose a custom residence time distribution, which can be very useful, particularly for some data-rich health studies. We haven't looked at hierarchical state charts. You can have one state that might cover, an overarching state might cover a single state and allow you an economy of adding out transitions and in transitions that, particularly out transitions that would otherwise have to come from all the substates. So we can have hierarchical state charts, and they're useful. You can group together multiple states, and you'll see that in some of the example models. We don't have time to discuss that because I want to finish the day with a discussion of projects, okay? But I hope this has been useful in getting you up to speed on some basics of building AnyLogic models. Tomorrow, ladies and gentlemen, we're going to be talking about agent-agent interaction. We're going to be talking likely about mobility as well and spatial embedding of agents and about the placement of agents in networks, okay? So that's all on the docket for tomorrow. Any questions about this material before we go to a little exercise related to projects? Questions? Okay. So I think I'll stop